suppose that E is the region bounded by z equals x squared plus y squared, which is just a nice paraboloid, and z equals y, which is just a plane. And I want to find the volume of E. So I'm going to do this as a triple integral. I know that that's just the triple integral of 1 dv. So I just need to figure out what are my limits of integration. Okay. Now, all I was given was two surfaces here. I wasn't given any walls, so that tells me that the floor and the ceiling for this region must meet. So I'm going to set them equal to each other. X squared plus y squared equals y. Set them equal to each other so that I can find the curve where they meet. That's going to, when I then project that onto the xy plane, that's going to be the boundary of the projection of the entire solid onto the xy plane. Now, when I see this curve, I'm seeing x squareds being added to y squareds. I'm thinking polar. So I'm going to go ahead and work with this bit in polar coordinates. So I'm thinking this is going to become the double integral of d, integral from bottom to top. I'm going to have to figure out which one of these is on the bottom and which one is the top of 1 dz dA. And I'm just already thinking that I'm probably going to express d in terms of polar coordinates. This would be r squared equals r sine theta. I want to solve for r as a function of theta, so I'm going to call this equation 1. I'm going to say if r does not equal 0, I can divide by r. And I would get r equals sine theta. That would be equation 2. Okay. Now, these equations, again, are not algebraically equivalent, because this equation 1 is true if r is 0 regardless of what theta is. This equation is not true if r is 0 and theta is pi over 2, because 0 does not equal 1. Hopefully we know this. Okay. But r equals 0 just corresponds to 1 point, the origin, and that is on the graph of this curve. Because if theta happens to be 0, that's going to make sine theta 0, so r would be 0. So the origin is on the graph. So even though algebraically they have different solution sets, these are graphically equivalent. So that tells me that r equals sine theta is the boundary of the projection onto the xy plane. So that's going to be my region D that we have right here. Now, I'm going to pause a second to just see if I can't visualize this a little bit more. I know z equals x squared plus y squared is just going to be a paraboloid that opens up like so. And I know that z equals y is just a plane. It's the extrusion of the line z equals y. Now in the yz plane, that looks just kind of like so. So it looks like what we're getting is just a portion of this paraboloid. I'm going to attempt to draw that a little bit nicer here. So this would be the plane z equals y. This would be the paraboloid. I'm getting this little portion of that. And when I project it onto the xy plane, what I'm getting is this disk bounded by y equals sine of theta. Notice the curve where the paraboloid and the plane meet is not in a plane that's parallel to the xy plane. Doesn't have to be. I still just drop all of those points onto the xy plane, and that gives me this disk. This portion of the plane z equals y isn't a disk. It looks more elliptical to me. But when I project it onto the xy plane, I do get this disk. Okay, Now this also helps me to see that it looks like the bottom surface is going to be the paraboloid and the top surface is going to be the plane. If I hadn't been able to figure out what this looked like, once I know that this is the region in the xy plane over which I'm integrating, if I want to see what's the top and the bottom function, I can just pick a point in this region to plug in. So if I were to pick, let's say, 0, 1/2. If I pick 0, 1/2, on the paraboloid, I'm getting 0 plus 1/4. On the plane, I'm getting z is 1/2. The value on the plane is bigger. So sometimes you can figure out what the top and bottom surface are algebraically. Sometimes you can do it geometrically. If you can do both, that's great. But you can always sort of fall back on whichever method you feel more comfortable with. Okay, so now I can say this is the double integral over d. I'm just going to keep that as d because I think I'm going to want to switch to polar when we get there. But now I know that we're going from the bottom surface is x squared plus y squared to the top surface is y, and I'm integrating 1 dz dA. So we'll have the double integral over d dA. That's our shell. I'm going to work on this inside integral. An antiderivative of 1 is just z, so I'm getting z evaluated between y and x squared plus y squared. So we'll have the double integral over d of y minus x squared plus y squared dA. Now if you remember, we actually learned how to find volume as a double integral. When we found volume as a double integral, what we integrated was top minus bottom. So if you set this up as the double integral over the projection onto the xy plane from bottom to top of 1 dz dA, after you do the integral with respect to z, you have exactly the double integral you would get if you were finding the volume as a double integral. You're just integrating top minus bottom. All right, at this point, I'm going to evaluate this double integral. I think it makes sense to switch to polar coordinates. If you want to, I'd encourage you to pause the video now, evaluate this integral on your own, and then just turn the video back on to check your answer. So I'm just going to pause for a moment. Welcome back. Okay, so we're doing the double integral over d of y minus x squared plus y squared, that quantity, dA. And remember, we said that our d was this region bounded by r equals sine theta. So that curve was r equals sine of theta. So if I'm going to switch this to polar coordinates, I want to remember that a circle like this is traced as theta goes from 0 to pi. Over that interval, sine of theta is always positive, so r is positive. So I don't need to worry about that. I need to be a little bit careful when I have r equals cosine theta, because that's traced over the interval from 0 to pi, but sometimes r is negative. So remember, if you're working with r equals cosine theta, you want to go from negative pi over 2 to pi over 2 instead. Here, 0 to pi is going to work just fine. And then for each theta in that interval, there's my constant theta ray. I can see r is going from 0 to the r value on the circle, which is sine theta. Now, I'm going to rewrite my integrand in terms of polar coordinates. So y is r sine theta minus x squared plus y squared is just r squared. And then don't forget dA is r dr d theta. So I need to distribute that r before I'm ready to actually do the integration. So I've got the integral from 0 to pi, integral from 0 to sine theta, r squared sine theta minus r cubed dr d theta. if I take an antiderivative with respect to r, we've got the integral from 0 to pi, r cubed over 3 sine theta minus r to the 4th over 4 d theta. Oops. And I'm evaluating this, sorry. I'm evaluating this between sine of theta and 0. Okay, so that's going to become the integral from 0 to pi. When I plug in sine theta, that becomes sine cubed times sine. That's going to be sine to the 4th theta over 3 minus, when I plug in sine, I'm going to get another sine to the 4th theta, this time over 4. And then when I plug in 0, I'm going to get 0. D theta. So, if I were to find a common denominator here, I can say that's the integral from 0 to pi, 4 sine to the 4th theta over 12 minus 3 sine to the 4th theta over 12 d theta. So I can see I'm really just integrating one copy of sine to the 4th theta over 12. So it's the integral from 0 to pi of 1/12, I'm going to just factor that out, sine to the 4th theta d theta. Okay, so that's an even power of sine. Even powers of sine or cosine, I'm always going to use the double angle formula for cosine. So cosine of 2 theta is cosine squared theta minus sine squared theta. Now notice this is sine to the 4th, but what I'm going to do is I'm going to just write that as sine squared theta times sine squared theta. Because the idea is I can now use this. This is showing up in my integrand, but it's tricky to integrate. That's easy to integrate. So I want to express this one in terms of that one. Let's get rid of this one. Cosine squared is just 1 minus sine squared theta. And then I'm still subtracting this. So this is 1 minus 2 sine squared theta. That was still equal to cosine 2 theta. So I'm going to solve for sine squared. So I'm going to add this over, subtract this over. So 2 sine squared theta is 1 minus cosine of 2 theta. Sine squared of theta is 1 minus cosine of 2 theta over 2. So I can plug that in here. So this is going to be 1/12, the integral from 0 to pi, of 1 minus cosine 2 theta over 2 times 1 minus cosine of 2 theta over 2 d theta. In the denominator here, I'm going to get a 4, which I'm just going to factor out. So I'll have 1/48, the integral from 0 to pi. And I'm just going to FOIL out the top. So that's 1 minus 2 copies of cosine 2 theta plus cosine squared 2 theta d theta. Now I'm going to split this up. These two parts I can evaluate pretty simply. This part I'm going to need to use the double angle formula again. So this is 1/48 integral from 0 to pi of 1 minus 2 cosine 2 theta d theta plus 1/48 the integral from 0 to pi of cosine squared 2 theta d theta. Now, what I'm going to do at this point is just stop the video because we've been going for a while and it's I'm not entirely clear on how long the videos are that I can upload to YouTube. So I'm going to stop the video here and we'll come back and finish off these calculations in the next video. So I will see you then.